organizers for setting up this wonderful conference, which I'm enjoying quite a lot. Well, while we wait for my slides to come up, I want to talk about moiré systems, more specifically moiré transition metal dichalcogenides, and how we can control certain properties in terms of displacement field in them.
Almost there.
Yeah, take your time.
Okay.
Yeah, there we go. Let me try, yeah. And I'm sure you've probably heard already about moiré materials, but I believe I'm the first one to talk about them here, so let me spend 1 or 2 slides on introducing them quickly. Generally, we call anything a moiré material which has such a moiré pattern, which you can barely recognize because of the resolution here. But you basically get a moiré pattern, and this moiré pattern should influence the physics we are interested in. They occur quite generally if you overlay 2 periodic structures. And here I'm showing 2 examples. This one would be two honeycomb lattices rotated by 5 degrees, and then you'll see certain regions which are brighter than others, and that's what's called the moiré pattern. And here on the right, you see a similar thing, which we get at 0 rotation angle because of 2 different lattice constants of these lattices. And you can think of this basically like an interference pattern of the 2 regular lattices that we overlay over each other. And then, of course, electrons who live in these materials will feel the difference in the potential due to this pattern, and that's how we can manipulate their properties to some extent in these systems. And in the recent years, this has really grown a lot, exploring the possibilities we have here. So I would say this has become a platform for both correlated and topological quantum materials. And the reason for this are maybe mainly that on the one hand we really have many, many possibilities just by combining all the possible 2-dimensional materials we have. And maybe more importantly, why this has become so successful is the high degree of control that we have in these systems. We can change carrier densities by just tuning a voltage knob. We can model different types of interactions, for example, through screening layers or the twist angle, etc. And this is why this has also been related to a simulation of correlated systems. And this is, I would say, one part of this field, simulating and studying corresponding model systems that we can, to some extent, realize here. But then there are also new phenomena which are really unique to having these moiré systems. Now, in the talk today, I want to concentrate on this first part, model systems, and you'll see that I will do basically what was called, I think, in this morning, elegant approximations. So I will do a series of approximations to end up with a somewhat simple model Hamiltonian that we can then study, which is still a very rich physics. Good, so now let me go into more details. I want to talk about moiré transition metal dichalcogenides, which is still a large group of systems because there are several TMDs. And we then have to be, when we say this, really careful about the details because it depends on them what type of model we will get out. Then first of all, we have to distinguish if we put two TMDs which are the same on top of each other or 2 different ones, so if you have homo or hetero bilayers. And then the stacking configuration is also important, which is called AA versus AB stacking, meaning that it makes a difference if you start with 0 or 180 degree twist angle. This is different to graphene-based systems. The reason is the bonding in the TMDs. Now what I want to talk about in this talk is twisted AB stacked tungsten diselenide. And this is motivated by these experiments from the Cornell group, where they built such a heterostructure, where we have this twisted tungsten diselenide layer, and then another layer which is used as a sensor, more specifically an exciton is used as a sensor for what's going on in this twisted TMD layer. And here you see a measurement of the reflectance contrast as function of the filling of our probe layer and the energy. And I want to focus on this 2S resonance, where you see that if we are at integer fillings, there's a blue shift, which points to having less screening, which means that there are interaction effects at integer fillings, so probably insulators occurring in these places. And then on top of that, we can not only vary filling, but the experiment also varied the displacement field, which will change the properties. And here you see the critical displacement field that was needed for saturation, one of the layers, and that one led to an increased layer polarisability that was measured compared to a capacitor model, and both of these effects point to strong interaction effects. Now I want to focus on just this point here, where we have filling of one hole in the moiré band structure. And at this filling, the experiment reported basically a paramagnetic response in the magnetization. So this is magnetic circular dichroism measurements. And if you look at the at the Curie-Weiss temperatures, they are slightly negative. So together with the observation that we have an insulator, this points towards the formation of local moments at this filling factor of 1 that have a slight antiferromagnetic exchange. And this is what we took as an input, and now to motivate the model we ended up studying with, I have to go into more details of the moiré band structure. For this, we need to take a step back and consider just a single layer tungsten diselenide, which is a semiconductor, and here you see the energy bands in the hexagonal Brillouin zone of one such layer with a band gap that is smallest at k and k prime points. And then there's also strong spin-orbit coupling in this system, which leads to something called spin-valley locking. So in the valence band, so if I am, say, at this valley minus k, and the valence band has spin down, this means that at valley k it will be spin up. So these are not independent degrees of freedom in a sense. Good, then we take two of these, put them on top of each other and slightly rotate. And because I said we do that in an AB fashion, we now have, say, from the top layer, the K valley with spin up in close proximity to the K prime valley with spin down. Because of we have now scattering that is more strongly between points that are close to each other, and these have opposite spins, definite spins, to a good approximation, this is suppressed, there's no hybridization between the layers. And because of that, spin remains a good quantum number in these systems. Layer, spin anyway, and then layer remains a good quantum number. And with all of these ingredients, we then still have the moiré potential, which leads to a backfolding of the bands because our unit cell is so much enlarged, and people calculated the corresponding band structure, which you see here in the mini Brillouin zone. And you also see that this red line fits the highest valence band of the moiré band structure quite well, and this red line corresponds to a triangular lattice-tight binding model. So all of these steps in the end mean if I want to study the physics that's taking place in this valence band, I can use a triangular lattice model with approximate SU4 degree of freedom, and then Hubbard interaction for the strong correlations. And the SU4 degree of freedom comes from layer, top, bottom, and spin up or down, which is equal to Vallée plus or minus. And this is, in the end, the model that we'll be studying. And we also will go to strong coupling, where the Hubbard model becomes the Heisenberg model. So the rest of the talk I want to spend on this four-flavor Heisenberg model and study what it does if we put it in a field to model the displacement field of the experiment. This was work done with my collaborator, Lorenzo Del Rey, from the Max Planck Institute in Stuttgart. Yeah, and I'm going to argue that this model has several sources of frustration, which lead to a very interesting phase diagram. And this phase diagram we've calculated with several methods. I'm going to walk you through them. Basically, they include more and more quantum fluctuations. Good. So with that, let's start. This is finally the model that we've studied. We have, as I said, we go to the strong coupling limit. We had filling 1, or in this limit, actually filling 3 is equivalent. And then we have this four-flavor Heisenberg model, which are nearest neighbor spins interacting and next nearest neighbor spins interacting. And the difference to the kind of usual SU2 case is that here we have the SU4 operators made of our four flavors, spin up and down, and layer, top and bottom. And then on top of that, I said we add the displacement field, which leads to such a polarizing term with field delta. And in our sign convention, this would favor the population of the bottom layer. Let me also point out here that this, in a sense, is a quite general model. If I shuffle around what I call flavor 1, 2, 3, 4, this would also model the same thing in a Zeeman field. Or I could imagine to model a population imbalance in cold atoms. All right, so now before we do any calculations here, let's look into what is known already about certain limits of this model. And the one limit that has been studied quite extensively is the model of a very large displacement field when basically only one of the layers is populated. Because in that case, it becomes energetically too expensive to populate the upper layer, so I'm back to the SU2 triangular lattice Heisenberg model. As you know, probably this model is geometrically frustrated if I have an antiferromagnetic interaction, and on top of that, if I add a next nearest neighbor interaction, there's also a frustration on that level. And this has led to such a phase diagram as function of this next nearest neighbor interaction. Some of the authors of this paper, I think, are even here. And you find that for small values of this next nearest neighbor interaction, there's an antiferromagnet with a 120-degree orientation between the spins. For large values, there's a stripe phase, which is favored by this J prime, and in between, there's a spin-liquid phase. I think the occurrence of the spin-liquid phase is kind of settled. What's not clear yet is the type of spin-liquid we have here. Okay, so then this was one limit. Now let's go into the opposite limit of zero polarization field. In that case, we have a full SU4 symmetry. Now, in this case, as I'm showing here, I can easily satisfy the antiferromagnetic requirement that I want to have different flavors on neighboring sides. And for the start, let's set J prime next nearest neighbor to 0. However, there's still a large degree of frustration, at least in a classical consideration in this system, because I can replace any of these flavors here by the fourth one and have a state of the same energy. So there's a huge degeneracy in the ground state. As soon as I add a J prime, this will favor such a four sublattice ground state in the system. And this has led to such a phase diagram that was suggested, where we have now in the quantum case, where we have a quantum spin liquid, presumably for small j prime, and then this 4 sublattice state for large j prime. Okay, so this is what we already know. Now as a next step, let's add the polarization field. And let's start with just a small field, again j prime equal to 0. In that case, I immediately want to form such a tripartite configuration, because it will satisfy both the antiferromagnetic requirement and it will be the largest value, it will lead to the largest polarization satisfying the field term. But still, I cannot get rid of this large degeneracy, because again, I can flip now this spin, for example, and do that to any other spin in the top layer and have a state of the same energy, because it doesn't change the polarization. So we still have this classical huge degeneracy, so still large degree of frustration, which promises to be interesting in the quantum case. And this is basically what we wanted to know, what happens in the quantum case if we study this field dependence with the next nearest neighbor interaction. And now let me walk you through these steps that we did to start answering that question. As the first step, we did a mean field theory, which means we set up an ansatz state, here such a product state, and minimize the corresponding energy that we get with this state. The state we ended up choosing is this superposition of the 4 flavors on each side for a given polarization PZ. And then we have these wave vectors here, 3 of them, QST, QP, and QSB, which will describe the spin order in top and bottom valley, as well as the relative, basically, density wave order between the layers, or if you like in a field you can call this an excitonic order. So QS top would be the wave vector of a spin density wave in top layer, QS bottom of the one in the bottom layer, and QP of the excitonic order. This state has a homogeneous layer polarization, which is in contrast to these flavor polarized states I was discussing previously on the classical level, but we can show that this state has always a lower energy than these classical states I was discussing, and becomes degenerate with them in the SU2 and SU4 limits. So in that sense, it's a good ansatz. Good. So here is now the phase diagram. We satisfy these limits that I've already discussed in the mean field case, and then we can see what happens if we change our polarization a bit. So in the SU2 scenario, say for large displacement fields, it means we start populating the top layer. And it turns out that in this case, we kind of continuously go from this 120-degree antiferromagnet in the bottom layer to the same thing with the ferromagnetic configuration in the top layer, and also a 120-degree configuration in the excitonic order. And this happens both at large and at small fields. And then similarly, we can expand around the stripe and 4 sublattice state, and it turns out that this also continuously kind of evolves with populating the other layer. The stripe will be accompanied by another stripe in the second layer, and a third stripe in the excitonic order in another direction, which is the 4 sublattice ground state. So you can already kind of guess that in the end the phase diagram is basically continuously connecting between these two limits. There's just a small deviation, which is an incommensurate order that occurs here. Good, so with this we can then use our mean field ground states to calculate the polarization of the layers as function of the field, and we did this for several values of the J prime. You see the result here. And we find in the basically the blue regions here of the phase diagram, the polarization rises linearly, whereas it's non-linear in this incommensurate state, and there's a first order jump going from crossing this first phase boundary. If I go to smaller and smaller values of J prime, the polarisability, which is basically the derivative here, becomes sharper and sharper, ending up in a first order transition at 0 J prime, and this might explain the increased polarisability that was seen in experiment. And note also that this is an interesting first order transition with a degenerate set of ground states, and which means you don't have any hysteresis. Okay, so this was mean field theory without any quantum fluctuations. As the next step, we wanted to add quantum fluctuations, and the next, maybe easiest thing to do is linear flavor-wave theory, which is the same thing as spin wave theory, just for four flavors. So this means that we rotate our mean field ground states in such a way that they all point up along flavor 1 in each of the lattice sides, and then we do such a Holstein-Primakov transformation where we introduce bosons to model our spins. And then in the harmonic approximation, we can calculate the excitations out of each of the states we have. And here I'm showing the result for these 4 points, so 0 J prime and different field values. And we basically, at least for large fields, get what we expect. Remember that we have this antiferromagnets, 120 degree, and then a ferromagnetic configuration, and this is exactly what you see here. This quadratic rise around gamma corresponds to the ferromagnet, which has a gap given by the saturation field and then becomes gapless below that field. And we have an antiferromagnetic branch which splits into these 2 antiferromagnetic branches when we start populating the second layer. Now, interestingly, these excitations here, if I lower the polarization, if I lower the field, become lower and lower in energy and soften down to a complete flat zero mode if I'm at this special value of 1/3 of the polarization. And this, of course, means that probably my ground state won't be stable because I have a zero mode in the system. So here you see also that in this sense, these zero energy fluctuations from this huge classical degeneracy even survive to this quantum level. Right, then we can go even lower in polarization where we had this degeneracy of ground states on the mean field level. And there is what's called order by disorder, so now on the quantum level a certain state is picked. However, we still have such a flat zero line here, so probably still not a stable ground state. And the only way how we can basically cure these zero excitations is by introducing a finite J prime, and then you see that it becomes gapped. And this in turn then allows us to continue the calculations without having to deal with infinities and see if the order parameter remains a good order parameter or if these quantum fluctuations destroy the mean field order. And so this is what we did next, and basically we found that in certain regimes of the phase diagram indeed the order is destroyed, or in other words, quantum fluctuations prevent the formation of order in these regimes. Here you see 2 examples along these 2 lines where our criterion is that the majority flavor stops being majority. And in the SU2 limit, this corresponds exactly to the magnetization becoming 0. And if we do this for the entire phase diagram, we see that for these larger values, the phases remain stable, but in between here, we have a large regime of a strongly fluctuating phase. And interestingly, this strongly fluctuating phase, where we seem to be quantum disordered, has phase boundaries in the SU2 limit, which coincide with the phase boundaries of the quantum spin liquid that was found in quantum Monte Carlo or DMRG calculations. So suggesting maybe this regime might host somewhere a quantum spin liquid, which we can then try to understand better in terms of the moiré materials. All right, then how much time do I have left? Okay, that's enough. So then, as a final step, we wanted to see how much of this phenomenology survives really to the quantum level if we do not some harmonic approximation, but really include all quantum fluctuations exactly. The price to pay is, so we did exact diagonalisation. The price to pay is we can only consider a relatively small system. In our case, that was 12 lattice sites. We also calculated the case for J prime equals to 0. And here you see the results now for the polarization as function of the field, which now has these discrete steps just because we have only a discrete number of sites in our system. But we can still obtain an estimate for the polarisability by just taking finite differences here. And this is what you see in the inset. And interestingly, there is still a peak around a polarization of 1/3, where we previously had this divergence. So this, in a sense, is consistent with this increased polarisability. And then, of course, we have more information available, and we can calculate the energy spectra in this system. And here you see the results for different polarizations, starting from 1 to 2/3 to 1/3 and 1/6. And as function of the spin, either in the bottom layer or in the total system, bottom and top layer. And basically, to summarize what you see here, in some cases, the lowest state fit a straight line, in others, not really. And this analysis goes back to what's called an Anderson tower of states, which tells us basically that in an antiferromagnet, these lowest lying energy states should be on a straight line, which then goes to 0 with system size. And this is what's happening if we have the 120-degree order. And we can also see that it only happens in one of the layers, in the bottom layer, and not in the top layer where we expect the ferromagnetic order. And then this completely breaks down also if we go to the special value of the polarization or even lower. So overall, this is consistent with the phase diagram I was showing earlier. All right, so this brings me to the conclusion. What we've studied is kind of a paradigmatic model, namely the four-flavour Heisenberg model in a field. And this can be realized, for example, in twisted transition metal dichalcogenides. Now, I think we find an interesting, very rich phase diagram with this interesting, strongly fluctuating phase where we have a quantum disordered ground state. And now in the future, of course, we would like to understand this better. First of all, we would like to know, do we really have these mod insulators we started with here? So this is maybe next step to do, going to finite temperatures and studying really the Hubbard model. And then it will be interesting to study this field tunability of a, say, putative quantum spin liquid, and maybe we can learn more about the spin liquids in these extreme limits and how they are connected doing this. Thank you very much.
Yeah, thank you, Laura, for your fascinating insights. The floor is open for discussions. I might start this one off. So I have an excitation question. So you made some analogy to spin wave excitation or magnetic excitations, and you indicated that you have now 4 flavors. So right. For magnetic excitation, it's pretty clear to me that you want to excite with a magnetic dipole radiation. Or with a magnetic component of an electromagnetic field. So how is this in your case, where you have these more complex flavors which are partially spin and partially
Yeah, so they should still react to magnetic fields, since there's also the spin dependence in them. And then the other question is how to study the difference in the polarization, right, in the charge degree of freedom. So there, anything, I guess, that would couple to charge, like an electric field, should also do the job. Yeah, what's very typical in these systems is actually kind of the measurement I discussed in the beginning, some optical measurements.
Okay. Alex.
Yes. Yeah, so my question is already on your last slide, finite temperature. What would be your estimate for an experimentalist, what the relevant energy scale of temperatures would be? Say scale to interaction or...
Right, so then we can basically go back to the experiments that were done, and I think this was a few Kelvin. I don't remember exactly, maybe 10 Kelvin or so.
More questions? Maybe I volunteer for a secondary question. No, please, here. Brace for impact. Alex, you have to throw.
Yeah, hi, thank you very much. So also from this experimental point of view, how would you control J prime? Or even not control, but how would you know what is your J or J prime?
Yeah, so in a sense, to be honest, this was a theory attempt because we started without, and then we realized we can't do any calculations because of this huge degeneracy, which will destroy our ground state. But I think even in reality, to some degree, we might be able to control by screening layers, right? And then varying the distance.
Okay. Then I see no more questions, and we unfortunately have to move on. That thanks both of the speakers of this session.